All right, cool. Hi, everyone. My name is Cunningham. As my lovely introduction stated, I am a senior software engineer at Second Spectrum. We're based very close to here in downtown LA in Little Tokyo. We work with the NBA as their official optical tracking and analytics provider. What that means is every time there's a live game, we have about 6 to 10 cameras, high resolution cameras in the rafters, recording everything that's happening. And from that live video capture, it first goes through a computer vision layer that is able to do object detection, so XYZ position for players on the court and also the ball. And then from the object detection layer, we have a machine learning layer that is able to assign meaning to those motions. So for example, given a certain pattern of motion, was that a dunk? Was it a successful dunk? Or if a player is in possession of a ball on one end of the court and they have 2 defenders at a certain distance, what's the probability, given what we know about these types of situations, that they might be able to make it in, things like that. So using that data, we produce full stack applications that are in use by the league, individual coaching staff on teams, and then also we have a consumer-facing product that is bringing that data to life in the form of live augmentations on top of video. We're working right now on this consumer-facing product, and it's released to some beta users, and hopefully that will be coming to devices near you soon. I am a full stack developer on the sports performance and analytics team. So what that means is we work with the data, the raw data that's coming out of our tracking layers, and we bring them to life in forms that can be consumed and read and used by coaches within the league. And today I'm going to talk about none of that. Instead, I'm going to be talking about 2 things. The rise in popularity of statically typed languages, strong statically typed languages, and then sort of a bit of theory about where that's coming from, because I think it's really interesting. And I'll full disclosure, prior to becoming a software engineer, I spent 10 years as a formal semanticist. I was a linguist. I was in a graduate program at Brown University, and that's how I first learned about types and the lambda calculus and category theory and all these things. And now these things are like popular or starting to become popular, and it's like so exciting to me. But yeah, let's start with the present day. So I think Gerard in his talk mentioned TypeScript. Yeah. For folks who are not familiar, these are just a few languages that are rising in popularity, and one of the things that's really cool about them is they are strongly aesthetically typed. What that means is when you write a bit of code, when you write a function, these languages will make you say what you intend the input to be and what you intend the return value to be. In the case of Elm, it's going to be very, very strict about this, and then in the case of Reason and TypeScript, it's a little bit more lax. But the point is, once you declare these things up front, now all of a sudden your compiler is able to check every time you use that function, if you're using it correctly, if you're using it with validly typed input arguments. And there are lots of benefits to this. Here are some. One, a reduction in runtime errors. So if your compiler can catch a lot of these low-level validation issues, you're in some cases, like in Elm, you're guaranteed that if your code compiles, it is at least never going to crash on a user. Now, there might be other like business level type bugs that happen along the way, but you're never going to get caught with an uncaught undefined in your console somewhere and then have to debug it like woken up 1 a.m. ops-genie alert going off and you're like, oh my god. Another thing that we've found is like really useful using these types of languages is that these type annotations that you add to your code actually also help you with creating self-documenting code. It makes your code a lot more legible and easier to reason about when you state up front. Again, like what do I expect coming in? What do I expect coming out? It also, along those lines, can help reason about a particular design. We've found, we use Elm in production at Second Spectrum, and one thing that we found really nice about a rich and robust type system is that we start by thinking about the types. And then from there, once we have sort of this ontological view of what our program is going to do and how it's going to do it, that drives development, as opposed to thinking about things like, okay, how am I going to represent the state of this thing? I guess I'll use an object, and then I guess this object might have these fields, but I have to get it right now because refactoring later might be a very, very painful process because I'm going to have to find all these places on my own where things are happening and make sure that I update them. And then that lends to my next point, which is that once you have these systems in place, you also have a more maintainable project code base. So another thing that we found on my team at Second Spectrum is that with languages like TypeScript and Elm, it's a lot easier for folks to jump back in and be able to add things, refactor things, without worrying about breaking something somewhere else in some other aspect of the code base that they never meant to break. And then all of this, just helps us sleep easier at night. Like I said, no one wants to get woken up in the middle of the night with some kind of alert saying that, like, some customer took the site down because maybe they inputted something that we didn't expect. So these are some of the benefits, but really what I want to talk about is the theory. Where do types come from? And I'll admit, given my background, I have a bit of an edge here. But I think that there's a really cool story about where types are coming from. And we're going to go all the way back to before a time of software engineering or computers at all. We're going to go all the way back to the late 1800s. At the time, what was going on was, so this is George Cantor, who created naive set theory, and then Gottlob Frege, who, using naive set theory, codified and created a modern language to talk about logic. He's kind of the father of modern semantics and logic. And what was really cool was, so at the time, right, this is pre-computers, pre-software, they were not trying to do anything that, or they didn't even know what we would do with this stuff. So the birth of naive set theory came out of a need that mathematicians and philosophers saw to be able to formalize some of the things that they wanted to be able to prove in mathematics. So for example, you can say 2 + 2 = 4, but that really doesn't mean anything until you know what 2 means, what plus means, what 4 means, and the hardest of all, what does equals mean? What does equality mean? Equality can mean a lot of different things, and in programming that sign can mean a lot of things as well under different contexts, depending on the language. So they came up with, George Cantor came up with naive set theory, which gave us a way of thinking about these things. Gottlob Frege created a formalism that people could actually use, and now all of a sudden mathematicians and philosophers have a language with which to describe some of these things that are happening in mathematics and philosophy. Super cool, right? There's a problem, and his name is Bertrand Russell. So this is 1901. So in 1901, Bertrand Russell, as he's looking through Gottlob Frege's Begriffsschrift the first time, he's like putting down into paper this logical language. He's looking through it and he realizes there's an issue with naive set theory. And the issue essentially is that under naive set theory, there's nothing to say that you couldn't define a set S such that it contains all the sets that do not contain themselves. That is very abstract, so let's ground that. A more colloquial manifestation of this paradox comes in the form of, this is also known as the barber paradox. So you can imagine there's this is barber in town, who shaves all the people who do not shave themselves. So the paradox emerges when you ask the question, who shaves the barber, right? Because if he shaves himself, well, then he doesn't. Yeah, and so on and so forth. You just go back and forth and back and forth. That's what makes it a paradox. This is like a huge bummer to Gottlob Frege. He spends the rest of his life really, really bummed out about this. He never leaves his small university town in Germany, and it's unfortunate because I think he thought that this was going to mar his record, but he otherwise produced such great work. But he's very bummed out by this. Meanwhile, what Bertrand Russell does is he starts thinking about this because it's kind of an interesting problem, right? So there are kind of two approaches to thinking about how we can get out of this paradox. So one comes in the form of actually just changing the rules of set theory, and this is what axiomatic set theory does, is it lays down some ground rules about what you cannot do, and that gets you out of the woods here. Great. Bertrand Russell, on the other hand, was not interested in doing that. He actually liked what naive set theory proposed. He just wanted to think about what other logical apparatus could we add to be able to help us from having to get stuck in these places. And what he adds is this notion of types. Basically what he says is, let's say you have different predicates and they can operate on certain kinds of things, and you can define what kinds of things they operate on and what they yield. Sounds familiar, right? And essentially, once you have types as a piece of logical apparatus, this is no longer a paradox, because this basically just says this doesn't exist. You cannot, the disbarber is undefined, essentially, and it's totally fine. Which brings us to this point. Cool, types were created to avoid paradoxes. They help us in software today, but they were created for this like very different reason, which is pretty neat, right? So we could stop there, we could, except you might also be wondering, like, why are we talking about paradoxes and logic when we get paid, many of us at least, get paid to not solve paradoxes but write code that's hopefully bug-free. So we need one more thing that sort of gets us back to the present. And this thing is called the Curry-Howard isomorphism. I apologize for the next slide and the really bad joke. Keep in mind the fact that I work for a sports tech company. So, yep, that's Steph Curry and Dwight Howard, but they are not the Curry and Howard of the Curry-Howard isomorphism. That's these dudes. Haskell Curry on the left, for those functional programming enthusiasts, he is who the language Haskell is named after, and also the notion of currying. And then over on the right is William Howard. Haskell Curry, mathematician, reverses. Mathematician, philosopher, and what happened was they had been working on different strains of thinking about how to create languages and logics that might represent the world. And they started a series of letters, a correspondence, where they would talk about the different things that they were working on, and what they realized was, and this is the isomorphism part, that what they were working on actually was very similar. They were intended for very different things, but there was a significant amount of overlap. What they were able to demonstrate, in fact, was different ways of representing the world. So things like the lambda calculus or combinatoric theory or category theory actually had a one-to-one mapping in terms of ways that they could talk about relationships between things in the world. In particular, they found that there is a connection between what you can do with logic and what you can do when you start thinking about the computation of programs. So for example, if you can prove something, you can also write a program for it, and vice versa. Likewise, if you can create the formula for something, or let's say a function for something, there's also a type signature that you can infer from it, and so on and so forth. So you get other things out of the Curry-Howard isomorphism, and at the bottom are some like really neat ideas where, let's say, if you can prove something is incomplete, you've also now suggested that it can get caught in an infinite loop. So there's this like one-to-one mapping between logic and computer science, cool, which brings us back to this idea of paradoxes. If there's this mapping between this idea of what we can do logically and what we can do with computation, it also lends itself to this idea now where we can think about paradoxes as both things that happen in like theoretical logic, but also things that can happen to our code, right? They're the equivalent of what in software we might think of as a bug, as a state that was not meant to be but has emerged. And so if types can help us with getting out of a situation where we're stuck in paradoxes, types can also help us prevent bugs in our code from emerging, right? What? Okay, so that's a theory bit. We're gonna go back to the present now, because I talk about how much I love like statically, strongly typed languages, and then sometimes there's always this person who's like, but what about testing? And my point is, but what about testing? You can still write tests. I think the cool thing about working with languages that are strongly typed or statically typed is that you have this compiler that takes care of this low-level logic for you, and now that means you can focus your tests to like focus solely on business-level logic, right? So I actually think that working with a type checker, working with a language that is strongly statically typed does not pull you away from having to think about tests. It does let you be a little bit lazier about the low-level stuff, but I think that's a win. I think that's a feature, not a bug. But yeah, so I think I throw this in there because I do think sometimes people are like, but this means people can be lazy, and I think that's a good thing. All right, that brings me to my shameless plug. I've been talking about all this theory, but as I mentioned at the very beginning, there are languages that are utilizing robust type systems, and it lends itself to a very, very pleasant programming experience. So shameless plug, I am a co-organizer for LMLA. Our next meetup is Monday. Like I said, Second Spectrum is super close to here, so if you made it here tonight, you can make it to Second Spectrum too. If you want more information, feel free to come up to me at any point tonight, but also if you look for LMLA on meetup.com, we have all of our details there. We're super beginner friendly because we realize that like most people have not drank the Kool-Aid quite as hard as we have. So if you've never written written any functional programming language before, or Elm, or touch any of these things, you are who we want to hang out with. Please come to our meetup. And we have an exciting speaker for next week as well. He'll be talking about the next release of Elm. I think this is my second to last slide. This is a picture of Haskell Curry. I just really like it because he's like, yes, now you are emboldened to use types and write type-safe code. And thank you. This is my name. This is how you can reach me. And yeah. And then I guess I'm doing questions also? All right.
Any questions? Intimidating topic.
Yeah.
How do you feel like your background as a linguist influences your day-to-day life as a programmer? How do you feel like it comes to day-to-day life?
So the question was, how do I feel my background as a linguist comes into play day to day as a programmer? So I think I fell into it, right? Like I am an accidental software engineer, and that like I spent 10 years as a linguist. I spent 10 years doing like the lambda calculus and category theory, and I thought that was going to be the rest of my life until I realized that I could also use these things in a different context and make things that people actually used and saw, as opposed to academic papers that no one would read, not even my advisor. So I think in that way, right, I think a lot of these like theoretical logical concepts, I think, are a great way for someone to get started in terms of like thinking about what an expressive language can do for you and what some of the alternatives are, and then also like what the low level like fundamental principles of computation are. I think when I first started working, I got a job at a dev shop in Venice, and I was doing like mostly front end stuff, a lot of like vanilla JavaScript, sometimes a little bit of jQuery, and then sometimes we did some Python stuff on the back end. So like I wasn't utilizing like a lot of the stuff that I had like come up doing in my research. And when I first started working, it felt really weird, and I was like, oh, mutating state, and I'm like writing these for loops, and then I'm shoving things into arrays, and this really feels like not what I was taught to do. But I liked being able to build things, so I was like, okay, fine, whatever. If this is what I have to do to like get paid to do this every day, I'll do it. But I always had this like nagging feeling in the back of my mind, like, oh, there's a better way to do this. So I'll say that now that people are starting to recognize that that's true, I feel so awesome about having been right this whole time. And it's I do think that like having a bit of like that theoretical background also sort of helps in terms of like understanding some of these things, and then also being able to translate it to different contexts and being able to like share that with other folks, because I do think like people who haven't done much functional programming, it's a steep learning curve. It's like so different and weird from how we're usually trained to think about these things, but having come from a background in linguistics, what I try to do when I am teaching people functional programming is ground it in something that we all know to do, which is to speak a language, right? And so it's interesting because some of the things that you can do in functional programming, like currying and composition and things like that, we do it every day in language. We just don't realize it. So I guess I think that's how that translates sometimes to my day-to-day. Yeah. Yeah.
What would be disadvantages of strongly typed languages?
Disadvantages of strongly typed languages. So I think the first one is that they're much slower, right? They slow down the development process because you have to think about these things up front, as opposed to, well, never maybe thinking about them until your application crashes somewhere down the line. I think that That's the one that has deterred a lot of people, is that, you know, JavaScript, for all of its problems, is just such a forgiving language. You can do whatever you want with it. And then if you've been writing it for a while, you probably have like some cool tricks and patterns that you've developed as a result of being able to manipulate or take advantage of some of these language features. And it's really hard when you move to something like Elm that is not just strictly typed, but also like there's in Elm there are no nulls. And again, that's like that's a huge paradigm shift, right? Because in JavaScript, you use nulls and undefines in certain contexts to actually like help you and like ease the speed of development in some ways. So I think those are some of the reasons that people have felt pain points transitioning from, you know, transitioning to like a strongly typed language to a language that's functional and things like that. But I think the rewards you see down the line, and once you kind of get over that learning curve, it's such a joy to write this code. The compiler in Elm is so expressive and also just so kind. The error messages are so helpful, and a lot of that is because of this like very robust and expressive type system that's able to, you know, have the compiler be able to infer so much about your program. Yeah.
How much Elm are you using in second spectrum?
Pretty much every new front-end project that we start now is written in Elm, and we haven't started going back and sort of, you know, taking care of like legacy stuff, but we're at a place now where across all of the different product teams, we're like super excited about it. So pretty much anytime we have a chance to use it, we'll try and make it an Elm project, yeah.